So this is the last practice set that we've got for AP Physics 2. And there's some things with electromagnetism. So here, this funny cartoon on the cover page um, basically shows that you get an induced voltage and induced current when you change the magnetic flux through an area. So you get a bigger change if you have more coils in the loop, for example, or if you move this faster. Having a strong magnetic field but no motion means you get no flux, no current, no voltage. So I'm going to go onto these pages. I'll upload them as a PDF as well. And I screwed up on a couple of these. You can see there's a lot of whiteout on this page, which is because I forgot I screwed up till later until it didn't make sense. So one of the things I would like you to think about is if you, I don't know why that's more in focus when I get in bigger. It's kind of weird. At any rate, I'll talk about that. But if you screw up on this test, you are going to have to work fast on it. Mine was mostly a mathematical thing. I think I still would have gotten most of the credit if it was this year's test, but I'll explain what I did. All right, for this free response, which is the only one that is from an AP2 exam in this set, when I go through it, like I say, we'll look at some of these things and see how they combine, and we'll see if it would be similar to, say, what we would have this year. I do think that you have two other problems. The other two that I've seen from AP2 free responses that have been released. So if you go back to the test where we had an electromagnetic free response, which was maybe like November-ish or something like that, I gave you a practice set ahead of time that had a practice free response, I believe, from like 2018 or 2017, and then the test itself had another one. So you want to take a look at those. If you go here, I'm pretty sure, yep, 18 and 19. So I don't remember which one was on your test, and I don't remember which one was necessarily the practice that I gave you, but I do know that I gave you both of those. If you want them and want the rubrics, let me know. So just trying to look at this kind of quick. This is taking a long time to open because it's an older version of Word. Oh. So this is from the 2018 exam. I like this because it's a paragraph, so I might share that with you again to look at. And then this is from the 2019 exam. Notice here they're going to be combining things with electric field and magnetic fields and things like that. Okay, I will probably post those. All right, with that being said, so for this one, you've got an area of each plate, which is given a distance between the plates. It says high velocity electrons are shot through here. They have an initial velocity of this, final velocity of this. It takes 1.49. You need to know that that's nanoseconds to get through. So nano is 10 to the negative 9th. So have somewhere where you know those prefixes and can look them up quick. So it says which is positively charged or which of the plates is negatively charged. Well, if the electron comes through here and then speeds up, it's being repelled from the negative plate. So the top plate must be negatively charged, the bottom plate must be positively charged. So electric field points from positive to negative, so it must point up. So it says that you have to support your answer with a reference to the direction of the electric field. There's several of these problems where we're going to have electron shot instead of positive charges. That's so you understand that the electric field points by definition from positive to negative. And so they're going to want you to differentiate the direction of field with, say, direction of force or acceleration, I think, which is why a lot of times I bet they're going to use negative charges. If this was a positive charge, obviously, and it was accelerating through here, then the top plate would be positive and the bottom plate would be negative. So for this next one, I'm going to have to shrink this down again. Find the magnitude of the electric field between the plates. There were 4 points out of the whole 10 on the real AP exam that were on this part, so I probably should have left a little more space. So the first thing you have to do to find basically what you need to realize is if you want to find electric field, that's force over charge. So you need to find electric force. In order to find electric force, you need to use the acceleration. In order to find acceleration, you need to use the data that's given. So there's a 3 or 4 step process here, which is why this is worth 4 points. So acceleration in this case is change in velocity over change in time, which is equal to 1.76 times 10 to the 15th meters per second squared. How I screwed up here is initially I just subtracted the accelerations, forgot to divide by that 1.49 nanoseconds. So that got me an incorrect answer. If I'd used that all down here, I should have gotten credit for the rest of these, but I would not have gotten credit for the part where I miscalculated acceleration. So I would have gotten partial credit. So the second thing is once I know acceleration, I need to find the net force on it. Well, that's Newton's second law, and yeah, you still need to know that, even though that was first-year physics, because it applies in so many situations. So there's the mass of an electron, that's something on your formula sheet. There's the acceleration I just figured out. That's the net force. And then finally, we use the net force to realize that's an electric force, and we use that to get the electric field strength. So this is the force I just calculated. This is the charge on an electron. And it's asking about the magnitude, so it doesn't matter about the direction in this point. So that comes out to 10,000 newtons per coulomb. This is a formula on your formula sheet to figure out the charge on each plate. I initially screwed up with this also a little bit. So it's charge on each plate divided by the area, and a constant is in the bottom. So it should make sense. You have a stronger field when you have more charge over a smaller area. So we rearrange that to get the charge on each plate, which is 2.21 times 10 to the negative 8th coulombs. For part D, it says now the electrons are leaving the bottom plate and they go into a box which has a magnetic field perpendicular to the page. So they already let you know it's into the page or out of the page. So it says the electrons leave the magnetic field over here, draw this. So this should be smooth. It should always be curving, I guess, as if it were going counterclockwise. So it should not be a straight or abrupt line, shouldn't be any corners or edges to it, something like this. The exact shape doesn't have to be exactly like this. It could curve a little more like that into a quarter of a circle, but something like that. So the key thing here, if you're explaining the shape, has to be part of a circular path, and that the magnetic force on the electrons are always perpendicular to their motion. That is the key aspect of this. So when we want to go back now and figure out the magnetic field into the page or out of the page, I use the left-hand rule because it's a negative charge and on electrons. So if I'm saying that my thumb points in the direction that's downward and the force has got to point to the right, the only way that works is with my left hand is if the fingers are pointing out toward my face, and that means that the magnetic field is directed out of the page. Going here, I modified some of this, so this is going to be more important to me. And honestly, I don't think this would be worth 3 points each on the AP2 tests. Back on the AP B tests, most of these were 15 points. So they were asking about specific amount of force here and maybe specific amount of field here mathematically. I doubt they're going to ask you to do that this year. They might ask you to set up an equation thinking about it, or to show how you would determine the field strength caused by, say, one of these charges, in which case that would be like the field strength here would be kq over this distance squared, and essentially you would add the horizontal components of it, so it would be that kq for that distance squared multiplied by sine essentially of this angle here would get you the vertical component. And then you'd add the same amount of vertical force over here, or field over here. But I don't think they're going to have you do that much of that. I think they want you to be able to explain things and understand them. So at this point A, when it's only asking about the direction, it would be directed upward. And the reason for that is that if you have something like this, where you've got an electric field, remember points away from the positive charges. So this would be the electric field caused by this charge over on the left, and we get the same thing magnitude-wise but opposite direction caused by this charge over here. So the net field would be pointing only upward. The horizontal parts cancel out. Okay. So I would be left. I'm going to take that out. Something like that. Okay. Now determine the net force on particle A when it's at this amount, or it says the direction. I think they asked you earlier or in the original question to determine the amount of force. Again, not that important at this point. You could figure that out if you knew this net field mathematically and you knew the amount of charge. You could calculate that by just force is equal to electric field times charge. Since E equals F over Q, F equals E times Q. So since this charge is negative and the field is pointing upward here, the charge will accelerate downward. It has a net force downward. Why does it have a net force downward? Well, I will tell you that. It is because we have electric field which points from positive to negative. The force would point toward the positive. So the force would point downwards, opposite the direction of field for a negative charge. And so therefore the acceleration would be downward. This is going to accelerate downward if you release a negative charge here. But once it gets past this point, where there's no net field and no net force, the acceleration will be upward. So it'll oscillate like this back and forth between 0.03 and negative 0.03 meters. Now, it would not be simple harmonic motion. It will act similar to that. But the reason for that is that simple harmonic motion has what's known as a linear restoring force. Well, here, if you have no force, here you're 0.3 meters up, you'd have a certain force downward. Here you'd have less force downward, but it wouldn't be half as much. It's not proportional in that particular way. So basically, you want to understand that this would oscillate back and forth. This one here, this particle is directed into the field. It's negative. Again, you're using a sketch here. It's going to curve clockwise direction, something like that. They didn't say this in the rubric, but I would not draw a complete circle. I would not draw more than half a circle, which would be basically just coming out somewhere over here. The reason for that is since the force is always perpendicular on the charge, it won't do any work on it, which means it won't speed it up or slow it down. And since the centripetal force is caused by the magnetic force, that means our centripetal force won't change. Well, if I had something going around like this, like entering and then going in a small circle here, that means the radius of the circle is changed, which means either the field strength is changed or the velocity is changed or something like that. So the big idea, curving around 1/2 of a circle or less. That actually is kind of important. Last parts here, calculate the magnetic force. So this is just simply a mathematical model. I was talking about the magnitude of it, so I don't need to worry whether that's positive or negative. Here an electric field, in this case, would equal the magnetic field, or pardon me, magnetic force. So it's asking you to calculate the magnitude of the field. So I could think of drawing a free body diagram or sketching it out. So at least initially, if the magnetic force is to the left, my electric force would have to be to the right. So those would have to be balanced. So if I figured out the magnetic force here, that means I need the same amount of electric force pointing the exact opposite direction. Okay, that's helpful because this is for a uniform field. Force over charge would equal field strength. So I put the force in I got up here. I should know the charge because it was given to me as 2 × 10⁻⁻⁻ coulombs. And I get a field strength of 3,000 newtons per coulomb. However, note that the field should point to the left because the force on the negative charge is to the right. So they're using negatives again, which I talked about in the first question, why I think they're doing that purposely. So showing that the acceleration is different than the direction of the field when you're talking about a negative charge. So the field is directed to the left, the electric force would be directed to the right. Okay. So if we have something like this, this is very calculation-y and not enough space, and I apologize again, it's from an old AP Physics B exam. So there are alternate methods for C and D here. Some of those are mentioned in the rubric. So the key thing here is if you're changing flux, if you're pulling this thing to the right, there will definitely be a magnetic force to the left. In this case, this is trickier, and I don't think they would do this year because I don't think this is a mix, or this. I don't think AP2 has like a lot of concept of friction with it. But there's also, if you're pulling to the right and moving to the right, it gives you a coefficient of friction and a mass of this rod, so it's like kind of lying on this thing and scraping along. So there would also be a force of friction to the left if you're pulling it to the right. So I don't think they do that this year, but they might do something else with another force opposite the direction of pulling. So maybe they'd be pulling something up against gravity in that case. So in that case then, oh, actually that's a good idea. They could give this rod a mass, have you pulling it all upward, and then there'd be a magnetic force acting down or against the change in flux, as well as a gravitational force acting down. So they could also have something where you have the magnetic force and a gravitational force balanced or things like that. So this is a good sample problem. At any rate, so you can use this formula, which is on your sheet, and that's basically caused by the change in flux because you're making this area in here bigger, so you're getting a lot more X's in this. Remember, with magnetic flux, we don't like change, so we don't like that. So you're going to induce a current in a direction that opposes that change. So another question they could ask here would be the direction of current in this metal rod, which I'll get to in a moment. At any rate, so the voltage across this, 0.75 volts, it asks for the current. Well, that's simply Ohm's law, which is V over R, in this case EMF over R, so that's 0.25 amps. Calculate the magnitude of the force required to pull the rod. This is important. So even though you don't have to draw free body diagrams this year, having some scratch paper where you mentally think that out may be helpful. So I know this pole is going to the right, and I know that the magnetic force will oppose it. Well, I also know that friction opposes motion, so friction will be the left. So essentially, force of friction plus the magnetic force would equal the force of the pole. Well, that's how I get force of friction. That's how I get the magnetic force on a length of wire. F equals BIL. Add those together, and that's how I get the amount of pole. How do I figure out the energy dissipated? Well, that's power times time in the resistor. So you could either do V times I for power, or I squared times R, or V squared divided by R. Any of those would work. But that'll end up giving you a certain amount here, which is somewhere around 0.2125, I think. Multiplied by 2 is 0.375. So actually, that's got to be less than that. That's 0.375. Wait. Okay, never mind. I screwed up how I was saying that, but this is the correct answer. Now to calculate the work done by pulling it, work is force times distance. I think that's something you should know this year, even though it was a Physics 1 concept. So FD cos theta, well, the pole is to the right, the displacement's to the right, so the cos theta doesn't mean anything. I'm going to use this force of the pole I got earlier, and the distance I can find by using velocity times time, which is 3.6 meters. So that tells me how much work is done. So basically, I'm doing this much work by pulling the rod, and this much energy is dissipated in the resistor. So there's a difference, which is a little unexpected when I did this. However, this part asks, explain why they are equal or unequal. Well, they're unequal, so that extra energy has to go somewhere. Most likely, it is dissipated in heat as this rod is scraping over this, because we do know there is friction. So, and 1 point of this was for correct units, by the way. So another thing I think they could ask here, maybe a little different, instead of the friction stuff, they could ask you the direction that the current was going in this rod. So if we think about this as being pulled to the right, like so, actually there's already an arrow there, I don't need that. Then what we have is increasing flux into the page here. That means to oppose that, we would want dots in this region, X's on this region. Well, using the curvy hand rule, we would find out that that would mean that we would have a current directed upward. We're talking about conventional current here, and directed over here, and directed downward here, and directed to the right down here. So again, if I have dots on the inside to oppose the increase in flux, that means I'm going to get a counterclockwise current, and that would be a question that could be asked. So hopefully those are good explanations.